Welcome. So today I'm going to just spend some time going over some of the important concepts for the chapter, or for the book that we've gotten at so far. And as a focus, I will use the test objective sheet, which is on the course website. So I'll go through just first off some of the formulas, which is what you see on the page in front of you. Most of these are equations that were on the first formula sheet. I deleted some, so if you're a careful reader of formula sheets, you remember right here, I had some formulas about resultant vectors, basically the component version of this right here. Since I'm not going to be asking you to resolve vectors into components specifically, then there's not going to be a problem about that on the test. I eliminated those formulas just to spread things out a little bit more. But I did leave this diagram on here because I think this is important, just because there won't be a specific question on the test in which you have to add vectors up like there was on the previous test, where the woman rode her bicycle to the north, and then to the northwest, and then to the east, and you had to figure out the resultant vector. There won't be anything specifically like that. There may be the need for you to resolve a vector into its component parts, and we've done that in some past videos, and I'll talk a little bit about that and do at least part of an example here that covers that as well. These formulas will be utilized a little bit, but primarily I think I'll probably have one problem in which this is one of these formulas will be the primary way to solve the problem. But there may be some times where you need to solve Newton's law here, Newton's second law for force, and then use that to find acceleration, and then use that acceleration maybe to find a velocity using this formula or that formula. So I thought it was important to keep these on here. So I just mentioned Newton's second law, net force equals mass times acceleration, and this word net here is really important. In fact, it's so important, I'm going to circle it. So if you say that force equals mass times acceleration, that's really incomplete, because any single force may not give you an acceleration. So this is an incomplete formula. A special case of this is just the formula for weight. Weight equals m times g. So if you know somebody's mass, I have a mass of about 78 kilograms or so, I can convert that to my weight in newtons. What's below this general formula are some specific formulas. So I mentioned the weight, a couple frictional formulas, so static friction or kinetic friction. And static friction, notice there's this less than or equal to sign. If you have a book sitting on a flat table, there's presumably friction between that book and that table. But if the table is not tilted and if nobody's pushing on the book, the force of friction is 0. If I push on that just a little bit, then the frictional force is tiny. If I push on it a medium amount, the frictional force is a medium amount. Pretty soon I can push it hard enough, and that is the maximum static friction. So that's where we have F sub s equals mu times the normal force. And once it's moving, when the two surfaces are moving with respect to each other, then it becomes kinetic friction. Another special case is if we have something moving in a circle, there is a force, a sum of forces, or a component of a force acting towards the center of that circle. Any two massive objects have a gravitational pull between them, but this pull is really only significant when we're talking about planets and stars and that sort of thing. The asteroid, forget what the name of it was, but the Rosetta spacecraft dropped a little probe, the Philae probe, on this asteroid. And it happened fairly recent from when I'm doing this recording, but of course this recording is going to last 1,000 years. So those of you watching this in 1,000 years, I'm going to be describing something that happened 1,000 years and about 3 weeks ago. But the probe landed on it, and it had an anchor that it was supposed to thrust out, and that didn't work quite right. So the probe bounced up, and I was just listening to a podcast, and because the asteroid is so much less massive than the Earth, that 200-pound probe, it was about 200 pounds, had a weight of just a few ounces. So you could have lifted up that probe, if you were standing on that asteroid, you could have lifted up that probe as easily as you would lift up a granola bar. Another special force here is actually a special case of friction, and that is drag. And drag is just a fancy name for friction due to fluids, and that could be fluids as in water, but it could also mean fluids as in air. So if you hold your hand out the window of your car, and if you hold your hand flat like this with respect to the window of the car, it doesn't seem to be pushed that much. If you hold it at an angle like this, it is going to be pushed a lot. That's because it's got a bigger cross-sectional area this way as opposed to this way flat. And of course, if you angle it, then you can make it go up and down. Look, my hand's a dolphin! Some of the other constants, and if the car is driving faster, your hand is going to feel a greater push, bigger drag force. Rho, that's the density of the fluid. So if all of a sudden you drive through water, then your hand is going to be pushed back a lot more than if you're driving through air. And this is just a constant that depends on the material. And then some math formulas. So just to briefly talk about the test again, the people watching this 1,000 years from now will not care about this, but our final exam, same room as the mid-quarter exam, Lind Hall room 215, 6 to 8. If you need a little bit extra time after that, that's certainly fine. There's not going to be anything scheduled at 8 o'clock in that room. Make sure you, once again, you bring your photo ID. A lot of you I would recognize, but I just want to make sure everybody needs to show me their photo ID. The final exam is comprehensive, but most of the points, the vast majority of the points, will be from the stuff that we've done since the first test. And you can see I didn't even list Chapter 3, so there'll be nothing at all from Chapter 3. Maybe one problem specifically from Chapter 2. And then you'll also use some of the Chapter 2 concepts when you're doing force problems as well. So the bulk of the test will be dealing with forces, so drawing free body diagrams, solving force problems, so writing the F net equals ma equation for your specific situation. So you should be reviewing the online office hour videos, so those examples, occasional lab activities, and I have those highlighted on the review sheet, and then of course problems from Expert TA, your homework. And the sheet that I just showed you here, that is what I will be providing you. You may annotate that, and just like with the previous test, I'll do a quick check of your review sheet and then put a special stamp on it. I'll be collecting the review sheet at the end of the test. And if you're interested in your review sheet back, you can just ask me about it, and when the quarter's over, beginning of the next quarter, I'll gladly give you your review sheet back if you like that as kind of an overall look of physics. This wasn't a big issue on the first exam, but just again to remind you that you need to show your work to get full credit for an item. Just doing it in your head, I don't know if you purely guessed or if you did the work in your head. So definitely show your work. Even if it's writing the formula and then writing the final answer for a one-step problem, that's fine. You don't have to do any sort of longhand multiplication or division. Okay, so the rest of the time I will spend a little bit going, just briefly describing and starting to set up some example problems for each step on the test objective sheet. If on the next time we're together, you want me to go over one of these in more detail, just send me an email and I'll do that. Or if you're watching right now, you can just put a comment in the chat box and I can spend more time on this on Thursday, because Thursday's video will also be reviewing for the final exam. So use kinematics equations with constant acceleration like those on page 57. So that is what we see in the upper left-hand corner right here. It's basically these equations right here. So to solve for an unknown, so an example, let's just quickly go over an example. I've got a few here to go over. So let's say we've got a hockey puck. It slides on a lake and comes to rest after traveling 200 meters. Its initial velocity is meters per second. What is its acceleration? So first off, does it really matter where we do this? It doesn't matter if we do this in Ellensburg or Seattle or South America. And for the most part, no. Maybe you could say if we did it at a super high elevation, the air is a little bit less dense. Maybe that changes the characteristics of the ice some. But for the most part, no. So that means we can say that x0 is equal to 0. And does it matter the time of day we do this? No. Maybe we're a little bit sleepier in the morning and we're not as good with the stopwatch if we need to stop, figure out time. That means we can set t0 equal to 0. If it did depend on the time of day, then we might say that t0 is equal to noon and t final is equal to 1 o'clock in the afternoon or something like that. X, which our book uses for x final, comes to rest after traveling 200 meters. We don't know how long it takes. It says initial velocity is 4 meters per second. Final velocity, there's no number here for final velocity, but it says that it comes to rest. So comes to rest is just a fancy way of saying that the final velocity is 0. So if it starts at 4 and ends up at 0, that means that it has an acceleration that is in that direction, so opposite the direction of motion. Velocity is from left to right as you're viewing it, so the acceleration is from right to left. We don't know the acceleration, and that's our target variable. So one of the ways that we can do this here is look at our formulas. And we know initial velocity, we know final velocity, we know how far it's traveled. So we need a formula that will help us with that. So this one doesn't have acceleration in it, neither does this one. This one has acceleration, it has final and initial velocity, but it also has time, and we don't know the time. This one, our same problem. It's got some things that we know, but it has something that we don't know, and that's time. This one, however, v final squared equals v initial squared plus 2a delta x, that is a good one for us to use because it does not have the time in it. The only unknown is the acceleration. So our strategy use the v squared equals v initial squared plus 2a x minus x0 and solve for a. So v squared minus v0 squared equals 2a x minus x0. So we can make note here that some things are already equal to 0. So v final, which I actually listed as v final. Which the book defines as v. So v final equals 0, and x initial equals 0. So we need to solve for a, so we get, let's go back to the color black again. So negative v0 squared divided by 2x equals a. So negative v0 squared, negative 4 meters per second squared divided by 2 times 200 meters. And look at the numbers here. We get negative 0.004 meters per second squared, or meters per second. Oopsie, sorry, I read my value wrong. We actually just get 0.04. Let's move this, space it out a little bit there. So that is the acceleration. Notice that it's negative. So negative, that's bad, right? What's bad is that I can't even spell negative. It's negative because it's pointing to the left. And we defined to the right as positive. And we did that right here. When we said the bigger number 200 is to the right of 0, that means that it counts upward to the right. So that means that any vector pointing to the right is positive, pointing to the left is negative. So There's our negative vector. There's our negative sign. So that's a sample of the problem type dealing with number 1. And folks who are watching, after each time, I won't ask if you have any questions, but if you do, please either verbalize them or put them in the chat box. If you want, you can put an emoticon in there too. You get a nice choice of emoticons and some odd things. You've got a soccer ball, a football. Put whatever emoticon fits your mood in there. If it's a happy face, great. If it's a sad face, not as great, but at least you're sharing it, and that's good. So number 2, given some of the following information, determine the rest. A sketch of the external forces acting on a system, the mass of the object or objects in the system, the net force acting on a system, the acceleration of a system, or a velocity versus time graph of a system. So this is a conceptual problem just to get you to think about some different ways to approach this. So here are some examples that I could ask, some types of things. So I could say, and I'm purely making these up on the spot, so I'm not going to use super difficult numbers. So a 10 kilogram object has the motion shown in this graph. I'm not going to write this brilliantly here, so forgive any poor writing. Of course, you've forgiven it already, right? So time, and here's 0. So this is 5, and so this is seconds. And here we have velocity in meters per second. So let's just say this is, what would be a good 20? That's too much. 10. So the 10 kilogram object has the motion shown in this graph. Determine the net force, and we don't know anything about the direction, so just the magnitude of the net force. So folks that are watching, how could we do this one? So we need to know net force. I've given you the mass. I've given you this graph here, and we want to determine that. So if we go back to our formulas here, so net force is equal to mass times acceleration, and I'm actually going to get rid of this little circle here because that kind of makes it busy looking. I gave you the mass. I asked you for the net force, but I didn't give you the acceleration. Or did I? Dun, dun, dun. I gave you a velocity versus time graph, but the slope of the velocity versus time graph is acceleration. So and so since this is constant, it's pretty easy to figure out. A equals delta V over delta T, which our book likes to simplify in basically that way right there. So in this case, delta V is 10 minus 0 meters per second divided by, this is really 5 minus 0 seconds, or 2 meters per second squared. So that means that the net force which equals m times a equals 10 kilograms times a, which is 2.0 meters per second squared, or 20. And let's look at this. Probably most of you remember what the unit of force is, but if you don't, that's okay, because whenever you're taking a test and you are not sure of the final unit, just do the algebraic product or quotient of the units. So we can just say that that is kilogram meters per second squared, but many of you probably remember that's 20 newtons. So let's see, let's figure out, let's just do one more here. All right, so that, and then we'll have a little frictional force. So let's say F sub n equals do we want it to be 1,000 newtons? Yeah, we'll say 1,000 newtons. And F applied equals 2,000 newtons. And mu equals 0.5. Determine M A F sub K F sub G and F net. And let's just say this is something that's being pulled along. So F applied is just along the floor. So it's a box being pulled or pushed along the floor. Okay, so how do we approach this? So folks watching the recording can actually stop the recording and work on it, and then start it back up again. Folks who are watching the video live, you're helping my ratings. Wait, I don't have any ratings. Hopefully you've started thinking about this. And there are a lot of ways to go about this. Oh yeah, so there are 5 things that we need to figure out. So mass, acceleration, frictional force, the weight, that's Fg, and then the net force. We can't necessarily do these in any order, but there are some things that need to be done before the other. So for example, right now, I could not tell you what the acceleration is. I mean, I could figure out the intermediate steps in my head and give you a number for the acceleration before I give you any other number, but I would have been doing some other things first. Similarly with the mass. So probably the easiest one to do first, I would say, is F sub g. So these can be solved in many different orders. Many, but not any order. So I'm going to start with F sub g. Since the box is being pulled along the floor, in the y direction, let's just make a quick xy coordinate system. Fn equals F sub g, so that's going to be 1,000 newtons as well. Right, so we've figured out that one. So the mass, if we know that, so we can find so F sub g equals m times g. Another way to describe that is W for weight. I should have done that to begin with. The other physics class I'm teaching this quarter uses F sub g, and that's the class I actually teach right after doing this video, so I was kind of in that mindset. So that's W. So M equals W over G, or 1,000 newtons divided by, and just to make the numbers easy here, 10 meters per second squared. So that's going to be equal to 100 kilograms. So now we've got that one. We can't figure out the acceleration yet. We still need to find the net force, and we need to find the frictional force. So we can find F sub k from F sub n. And again, the class that I'm teaching here soon uses F sub n rather than n. Oops, wrong one. So I'm going to just put that on here as well. So f sub k equals mu times f sub n, or mu, and I should have said mu sub k, equals 0.5 times f sub n, which is 1,000. So that's 500 newtons. The applied force is 2,000. So we know that F net is going to equal F applied minus the frictional force, or 2,000 newtons minus 500 newtons, so that's 1,500 newtons, and that's going to be going to the right. And then finally we can find A. So we found that, we found that. So 1,500 newtons divided by m, which was 100 kilograms, that's equal to 15. And if you forget, just say 15 newtons per kilogram. Or 15 meters per second squared to the right. The important thing about this objective is being proficient with multiple representations. We've talked about that before, this idea. So we've got, you need to sort of go between a sketch, some numbers such as mass and net force, and a graph. F net equals ma is a deceptively simple equation, but you can build a lot of equations from it. So let's say here we are parked on a hill. It's a pretty steep hill to be parked along. And that's a certain angle theta. And we want to sketch the forces. So free body diagram of the car. And then sketch the net force in the x direction, which can also be written as some of the force in the x direction, and some of the forces in the y direction. So first we need to sketch that. And for this, I want to have a tilted coordinate system. So note the x-axis is parallel to the hill. All right, and let's say there's some friction. So the forces that we're going to have here are gravitational pull of the Earth, contact push of the road, which I could have made a little bit longer, I think. And then let's say there's some friction. The hill here has an angle of theta, so that means that this is also theta. And there are two components here for the weight. And Wx and Wy, where Wx equals, so that's the side opposite theta. That's going to be W sine theta. Wy is the adjacent side, so that's going to be W cosine theta. So then writing the equations, some of the forces in the x direction, we're going to have Wx minus F sub k equals max, and we could also have written here that W equals m times g. So m g sine theta minus Fk equals max, some of the forces in the y direction, n minus Wy. And now this is going to equal 0 because there's no acceleration up out of the road or into the road. So the only acceleration is parallel to the road. So n equals W sub y, which equals mg times b cosine of theta. And if we wanted to find a sub x, we can relate the equations. With F sub k equals mu sub k times the normal force. And actually, let's go on to the next one. So we can solve some problems with this. If we wanted to figure out the acceleration for this one, we've got mg sine theta minus fk equals max. And we know that Fk equals mu sub k times the normal force. We also know that the normal force is mg cosine theta. So F sub k equals mu sub k times mg cosine theta, and then we can plug that in up above. Mu sub k mg sine theta equals m a sub x. So notice gloriously the m's cancel. And oops, mu sub k, sorry. That's mu sub k mg cosine theta. So that allows us to find A. If we wanted to figure out the velocity at the bottom of the hill, of 200-meter long hill, if the car starts from rest. So we can use v squared equals v0 squared plus 2a x minus x0, where, there we go, there's our target variable, and this is equal to 0 because it says if the car starts from rest. So I gave myself some extra space to solve it, but I think I squeezed pretty much everything in here. I used the definitions of friction described in the text to determine the force of friction using Newton's second law of motion given the appropriate information. That's what we just did. So we just did this with the ramp problem. So use drag force to solve for an unknown. That's really just going to be a plug-in type equation. So just using this equation right here. So I'm trying to make that D better here, but I didn't do a very good job. We get in the zone. Beautiful. So this is going to be one where I could just simply give you these numbers. I could say that a certain object is moving along with the velocity. You might have to figure out the cross-sectional area. I'd give you these densities and this constant here. I could also ask you, and this will be the last one I'll talk about, and then I'll finish the rest the next time we're together on video. But I could say, how does FD change if you double velocity, if you double cross-sectional area? So FD equals 1/2 C rho A times V squared, again, just based on our formula. So now the new one, we'll call that F prime, is 1/2 C rho A 2V squared. So the ratio of F to F prime, so 1/2 C rho A C rho A times V squared. So we've got a lot of things that are going to cancel. So both the top and the bottom have the half. This is just a constant. If we're talking about the same fluid from trial 1 to trial 2, that's a constant. If we haven't changed that, that's a constant. So V squared divided by V squared. So we end up with two squared over 1, or 4. So if we double V, the force increases by a factor of 4. If we double A, A just has the first power, so this is basically just the first power. So if we double that, force doubles. All right, so that is the first 6. I'll work on the last 4 the next time we're together. And then if folks have any questions about the first 6, feel free to ask those. But otherwise, I'll stop the recording, and I'll see you virtually next time.